This conference will now be recorded.
Alrighty, so today our speaker will be Adam Stonewall. He is a surface water specialist at the USGS Oregon Water Science Center. His work includes flood frequency analysis, hydraulic, hydrologic, and water quality modeling, and the detection of non-stationarity. So Adam, if you want to go ahead, we'll proceed with your presentation. Thank you.
Thanks for having me, and it's exciting to be here. Um, this is a relatively short presentation, about 30 minutes or so, and I'm happy to take questions at the end, obviously, but this all is related to some work that we did with the Oregon Department of Transportation, ODOT, um, tied to an area in the Siskiyou Pass in Southern Oregon. So with that intro, let me start off. The outline for the presentation is pretty standard. We're going to cover some basic background about why this study occurred and what we're hoping to accomplish with it. I'm going to talk about SELDM, which is the model we use to estimate water quality exceedances and concentrations and event mean concentrations for the basin, and then the standard methodology results in conclusion. So a bit of background. Most of you, I assume, are not from Oregon. But on the West Coast, we have one main artery of highway, which is I-5, and that runs up and down the West Coast between 50 to 100 miles from the coast itself, actually. So it's usually fairly temperate. And that's where quite a good of traffic, all kinds of trucks, goods movement, all the way from Canada to Mexico, goes up and down that highway. And for most of it, it's pretty safe, but the highest part of that is the Siskiyou Pass, which is in Southern Oregon, very close to the California border here. And historically, ODOT has not used road salt. They used magnesium chloride as a deicer. And lately, since around 2012, they started to experiment with road salt, sodium chloride, with the idea being that maybe using that in addition to the magnesium chloride could be a way to provide safer highways and hopefully not impact the environment in a negative connotation. So why they wanted to study this particular basin was because it's a major highway, so there's a lot of traffic, as you might imagine, and a lot of salt chloride needs to be applied. But also, it passes through some pretty small basins, some small watersheds. So, as you might imagine, the larger the highway and the smaller the watershed, the the less dilution is happening to the highway runoff. So this is like a test case to see, quote, kind of how bad are things getting with the amount of road salt being applied. So these two basins we studied, Wall Creek and Carter Creek, hopefully you can see my cursor. These are fairly small basins. They're both less than a square mile in size. And ODOT and the Oregon Department of Environmental Quality, DEQ, had some preliminary sampling they'd done and had some concentrations they were a little bit worried about. So they kind of hired us to come in here and kind of throw some modeling at it and try to get a better understanding of what we should expect for future years. The other idea is they want to be able to take this approach and implement it in other watersheds where they're thinking of also adding road salt to the formula. So in a perfect world, the lessons learned here can be applied elsewhere in the state. So I'm not going to go over all of the purpose and scope here. There's a lot of text on this slide, I know. But I do want to emphasize that we were looking at road salt, which of course is sodium chloride, and then the magnesium chloride too, because the chloride's the main interest. So I'll just focus on the chloride here in this presentation and kind of ignore the magnesium and sodium for the most part. And I also want to highlight number 2 here. I'm going to mostly talk about the water quality standards and how often we exceeded those as opposed to, the BMPs and other things that we looked at. And then last of all, I want to talk about the locally collected data we had. So ODOT was a very good cooperator, that they actually funded quite a bit of local data collection for this modeling effort. That's not always the case with SELDM. Um, so this is kind of more of the gold standard. And part of the analysis was saying, okay, we collected all these different data. Which data proved most useful for what we were doing? You know, if we didn't have the precipitation data, what would have happened? Or if we didn't have the highway runoff data or the streamflow data. So we kind of had a sensitivity analysis of what data was most imperative for this analysis as part of this too. So a bit about SELDM, stochastic empirical loading dilution model. So the key word here is stochastic. This is not a physically based model. We're not inputting time series where you try to recreate historic events. What we are doing here is getting uh, statistics for different hydrologic parameters and trying to replicate a distribution of what we might expect in nature, so to speak. So it's really a mass balance model at the end of the day. You've got your upstream area here, you know, upstream of the highway, and of course you have a concentration and a amount of stream flow, and that is your load. That's your incoming load. And of course the highway is kind of similar. You can think of it as its own little stream in a way. And there's the highway runoff, which of course is usually higher in whatever water quality constituent you're looking at than what you have upstream. And then of course you do the standard mass balance and get a downstream concentration and load. It gets a little bit more complicated when you look under the hood. Basically, all of these different parameters are described by a distribution of sorts. So if you think of uh, the mean and the standard deviation, the skewness, you know, that's how you define the population. And so for any given storm event, you may have a high upstream concentration or a high upstream storm flow or a low one or somewhere in between. And some of these are correlated, right? You tend to have higher concentrations with higher storm flows. So there's a lot of interactivity between the different variables, but you can just picture these as concentrations of there's a population of these as opposed to a time series is the main takeaway here. As far as the model inputs, they are plentiful. A lot of these are kind of fixed. So things like the drainage area of the upstream basin or the slope of the highway, those are not going to change from scenario to scenario within the model, right? Things that could change are some of these statistics, for example. So how many storm events per year, or uh, you know, how the concentration of the highway runoff. Things like that are not going to be constant from storm to storm. So a lot of these are just constant variables that are in the model. A lot of these are statistics that are defined by those population parameters. So I want to kind of talk a little bit about the different levels of analysis in SELDM. I kind of like to think of it as three different categories. The level one is kind of the out of the box level. It's what you want to do for a back of the envelope estimate. Maybe you'll do a level one analysis and find that you're 2 orders of magnitude below any potential problem. So you can kind of say, well, even if these numbers are pretty far off, I'm still feeling pretty confident. It's not meant to be a final answer, but more of a back of the envelope quick analysis. And a lot of the data in there, a lot of the inputs are already preloaded. So I'll give an example later, but a lot of these are just derived from national and regional data in a way that makes it very easy for the user to come in there, put in there lat long, and then it tells you what what the precipitation is going to be or something along those lines. A level two analysis is probably the more standard way to utilize SELDM. And with that, you're looking at regional and local data. You're making informed choices on which data you use and how you use those data. There could be some manipulation of the data. And when you do that, you tend to have a lower variance of results. So you have a little more firm idea of where you're going to be at. And of course, results tend to be better. It's not a guarantee of that, but that's the general idea at least. The level three analysis is kind of the gold standard of the analyses. Basically, if you have local data on the ground, you can have those as direct inputs for how much upstream storm flow we have, or how much highway runoff, or the concentration of chloride in the highway runoff, things like that. The problem there, of course, is data collection is expensive. It takes time. Ideally, you want to have 10 to 100 years of data, and that's not realistic. People aren't going to pay for 40 years of streamflow data before you do this analysis. So a lot of the level 3 analysis is really a hybrid level 2 and level 3, where you take a couple years of data and then kind of massage those data with other regional data to get better information and more informed decisions. So I'll call it level 3, but just keep in mind that it's a little bit of a hybrid, to be honest with you. And ODOT was, like I said, a great cooperator, and they actually paid for quite a bit of that data collection before we actually started the modeling efforts there. So a quick example of how this works. For precipitation, uh, this is uploaded with a rain zone precipitation statistics. So here's a blow-up of that model. So we're here in Southern Oregon. Hopefully you can see my cursor. And as you can see, this is a pretty big region. It covers a lot of California, a tiny bit of Nevada, a good chunk of Southern Oregon, but it's also fairly close to this region 15, the Pacific Northwest. So right away, you can already think, well, how representative is this point compared to this whole region as a whole? But SELDM comes preloaded with those precipitation statistics in the model. If I just put my lat long in there, then SELDM knows I'm in region 14, and it'll pull up those statistics, and I can use those as a default. If I want to do a level 2 analysis, I may have something like this. So all these raindrops represent NOAA precipitation gauges. And our area here is where we actually conducted this analysis. So you can see we have one gauge that's the closest. We could use that as the gauge and say that's our regional approach. Carter and Wall Creek are in a bigger watershed called Bear Creek. We've got 3 gauges in that. I could use those gauges and say, well, that's a regional approach. I could have this poorly poorly drawn polygon and pick these handful of gauges. Maybe these are varying elevations, so they have some that are higher and some that are lower, some that are west, some that are east. This isn't good because I got more to the west than to the east, and there's a rain shadow effect here. But you get the idea. You have to make an informed decision on how to utilize these data. And then finally, level 3, in this case, was the installation of a heated rain gauge. This was attached to a building in the ODOT ware yard in the actual Carter Creek Basin. So that worked out very well for us. And it melts the snow. You get snow water equivalent precipitation data right away. And we were able to utilize that, pair it up with that local long-term NOAA gauge, and get good estimates of what 40 years of record would look like, essentially. So there's a lot of information in here. I don't want to cover the whole slide, but the basic premise is that we had different levels we would try for different analyses. So we have one where it's all level 1, or as close as you can get to that, some where it's all level 3, and some in between. And the idea of doing that is that you can manipulate what data we have or what data we're not using to figure out how effective those specific data were in affecting the results. It's a sensitivity analysis of sorts. So for example, going back to our precip example, SELDM scenario 4 here is kind of the standard level, but we upgraded the precipitation, I guess this is level scenario 5 actually, to level 3. And so we could see, well, how much does that improve our estimates compared to the gold standard version where everything's level 3. So that was part of our approach here. Moving on to methods, like I mentioned before, sampling is expensive, so we couldn't sample everywhere. We kind of just had a downstream point for sampling specific conductance. We use that as a proxy for chloride. There's a great relationship between conductance and chloride. But we put most of our efforts here in the Carter Creek, the smaller basin, which you'd expect to have higher concentrations because it is smaller and has a similar amount of highway running through it. There's a tributary that accounts for most of the drainage area where we had conductance coming in. So we had a probe there where we had a good idea of the level of conductance prior to the highway. It flows west to east here. Here we had our precipitation gauge near the southern border of the watershed. Here we had this cloverleaf. You see this little inset diagram here. Here we actually measured runoff from the highway in this little cloverleaf area. It was designed to drain pretty much everything on the east side of the highway, whereas the other cloverleaf drains from this west side of the highway. And from there we could get concentrations, we could get amounts of flow, things of that nature. We also had an auto sampler there, so we could get samples when we weren't able to be there personally, which is important given the flashy nature of highway runoff, how quickly it comes and goes. And also, of course, a lot of that happens during the winter when it's very dark and kind of dangerous to walk through some of these highway areas to get to these spots. Then lastly, we had a downstream gauge where we had conductance measured, another sampler, and we had our stream flow measured. We could kind of use that with a drainage area ratio approach to estimate stream flow in other parts of the basin here. So moving on to results. This is part of the more regional approach. We actually did a random sampling of, I think it was 40 different highway stream intersections throughout the greater Bear Creek Basin. The idea being here, we could get a good estimate of what upstream concentration should look like. We basically took all the highway and NHD crossings and removed all the zero stream order crossings, since those are usually dry, especially in the summer, and focused on 1 through 4. And then we kind of made the distribution match. So if you have, say, 40% of your crossings are for first order streams, we had 40% of our samples through those first order streams. And we got pretty reasonable results. I'm going to focus on chloride here, like I said, mostly, but this is in log scale on the y-axis. So, we kind of had a median a little bit higher than 10. The quantiles didn't really spread much. They're below 20 and around 2 or something like that. And I know the scales aren't comparable because of the log scale, but you can kind of see that for magnesium, sodium, they were kind of similar. Interestingly enough, these 3 outliers are all the same site. Just by the randomness of the sampling, we had one site downstream of a landfill, and we didn't want to exclude it just because it was a landfill. So that kind of skewed the result just a tiny bit. But anyway, that was kind of an interesting part of the result. And then here's the relationship between chloride and conductance, R squared of 0.7. I know R squared is not the best metric, but it's easy to understand. And you can see that it's generally a pretty consistent relationship, but there is some variability throughout that greater Bear Creek Basin. Moving on to the same relationship, but with the highway runoff, you can see here we've got a very tight cluster of samples looking at chloride versus conductance. And this is kind of to be expected, right? This is the runoff from the highway. It's the same substance being applied to the highway, the same geology every time. The R squared is kind of inflated because these are not all independent samples. Some of these come from the same storm event, but even taking these away, there's a pretty tight cluster here. And the ones that are a little bit off typically happen early or late in the event itself. So you picture an early event, there's a lot of like first flush, higher concentration. So that's where you have a couple of these. And then late events are ones like this where it's a lot of the chloride's already been washed off, or maybe it's later in the summer when there's not as much being applied to the roadway. So, but in general, we felt very good about this relationship, and that our ability to predict chloride with conductance was pretty solid. So moving on to the modeling results. There's a lot going on here, so I'm going to try to, I know statistics can be kind of dry, I'm going to try to make this interesting as much as I can. What we have here is 3 different figures, And the one on the far left represents scenario 1. So this is the out of the box, back of the envelope estimate where we really don't put a lot of effort into this. We just kind of are trying to get a quick estimate of the results. Scenario 2 is the regional one I talked about. We're actually doing some work and plugging those data in. And scenario 3 is that gold standard where we take all the local data and plug those into. And then the different boxes are highway, upstream, and downstream. Ideally, I would have put the upstream on the left side, but uh, too late now. That's a done deal. So you can see, of course, that the highway is always the highest concentrations, the upstream is the lowest, and like you'd expect, the downstream is somewhere in between. These numbers here are medians, but I want to point out the numbers down here too, which are the mean values. And you might notice they're not that close on a lot of occasions. So if you look here on this level 1 analysis, our median value is a little bit less than 70, 67, and our mean value is 700. This kind of blew my mind at first, but that's the nature of the distribution. There are so many high outliers, and the outliers are so high that our median and our mean are nowhere close to each other. They're actually an order of magnitude apart. Um, as you move to the upstream, it's not quite that discrepancy. It's less than twice the value, and then it's in between, of course, during the downstream. So the important point here is as you move from less information to more information, that ratio shrinks quite a bit. We're going to full order of magnitude in the upstream, highway concentrations here, whereas on level 3, we're going from about 300 to about 500. So we're really narrowing that amount of uncertainty. We're getting a lot of that variability reduced, which is one of the main benefits of this modeling and adding those data. And even going from um, from the level 1 to level 2, they're more minor reductions, but they still occur too. The amount of variability that we reduce here. So moving on to, this is a lot of the same information, but in table form. But I kind of wanted to highlight this ratio here. So this is what you have on the upstream end, and then the downstream end, and that's the ratio of that. So in other words, using level 1 analysis, we would have estimated that the concentration of chloride was 21 times higher upstream or downstream versus upstream, and that's the result of the highway influence. And as we added more data, we saw that ratio shrink and shrink until it got down to 8, which was still substantial, of course, but there's a big difference between 21 versus 8 here. So moving on to the water quality standards, the EPA defines that as 860 milligrams per liter for a 1 hour concentration that should not occur more than once every 3 years on average. So the way SELDM works is it uses event mean concentrations, and these events are typically longer than an hour. I think they're pretty much always longer than an hour in our case. So keep that in mind as we go through these results, that um, even if we have an event mean concentration of say 800, and you think, well, okay, that's below the threshold of 860. If it's a 5-hour event, there's pretty good odds that 1 or 2 of those hours at least were above the 860. So it's a bit of apples and oranges comparison. This is like the low end of the problem as opposed to the high end, but it still gives us a good idea of what's going on in the basin. If we had more funding and more time, it would have been great to actually try to analyze and find a relationship between those EMCs and those peak values for each hour, but that was beyond the scope, unfortunately. So maybe in a future project, we might look at that more closely. So I know people are not always well versed in probability plots, so I'm going to go through this really quickly just so people have an understanding of what we're looking at. Here on the, what we have here are all the event mean concentrations. Each dot represents a SELDM run where it simulated an event. And you have multiple events per year. I think we had something around the low 40s or something in the case of this study. And of course, we sample from simulate multiple years of data too. So I think it was also around 40 years of data for this. So over 1,000 events were simulated, and each one of these dots represents one of those events. In this case, the blue dots are downstream, and the whatever color that is, kind of orangey, browny dots are the upstream, and the blue are the downstream. And the y-axis, of course, is the concentration of chloride. It's in log scale, so it's a little bit hard to intuit sometimes, but these are order of magnitude increases as you go up. This horizontal line is that 860 milligrams per liter that I referred to in the last slide. So this is what we're trying to avoid, is being above this line. And then down here, I know these numbers may look kind of wonky, but this is the exceedance probability. So basically, if we have an example of this upstream EMCs, if we say this 0.5, that's half the time. If we go up here, we see this is a little bit less than 10, maybe around 7 or 8 milligrams per liter. That means half the events, the upstream concentration was above 7 or 8 milligrams per liter, half was below. If you go over to here on 0.9, that means 90% of the events were above, say, 2 milligrams per liter or 3, and the other 10% were lower. And these numbers are not evenly distributed because that's the way probability is easiest to observe visually. If these weren't, these lines would be very slanted and hard to kind of decipher. So that's why you have these kind of unusual patterns on the x-axis. This vertical dash here shows the percent exceedance probability we need to actually achieve these USGS standards. So looking back at these dots here, if you imagine this being a line instead of a series of dots, if this actually connects with this vertical or horizontal line, this 860 milligrams per liter standard, to the left of this vertical line, then we are achieving our desired result. We're below that standard, right? Whereas if it's to the right, we are not achieving that. So if you imagine this blue line running up through here and say hitting this right at the 0.5, that would mean half the time we're exceeding this 860, half the time we're below it. And we don't want that, of course. We want to be down here where we're at, luckily. So now that I've explained that, moving on to the actual results. Here we have level 1, 2, and 3 in blue, orange, and I guess green, respectively. And the main takeaway here is that you can see with each increase of information, we decrease the variability in our results. We have more confidence in that. In these very high values, as we add more data, those high values become lower. The level 3 actually is primarily below this standard. And conversely, on the low end, we're also seeing the highest values for level 3. We're just reducing that variability. So using the standard here, if we did level 1 analysis, we actually hit this right around 0.023, which means 2.3% of the time we're exceeding that 860 milligrams per liter. Whereas level 2, we're right about at that level, which is around 1.1%. We're pretty much on that line. And then level 3, we're actually well below the line. It's kind of hitting out here off the chart, actually. We don't go to 0 because of the nature of this plot. Having said that, there's a fair amount of uncertainty in these results, right? So you wouldn't want to, be at 1 and say, well, 1.1 is our target, we're fine. This is very close. And as I mentioned before, this is apples to oranges comparison. So realistically, both of these would probably, suggest that we're not meeting this criteria. This one's more up in the air if you actually had the 1 hour results as opposed to the event mean concentrations. I included this because this is just an example of how it's not always a uniform decrease in variability. This is kind of a similar plot, but instead of looking at event mean concentrations, we're just looking at the upstream flow volume for the different events. And I found it interesting that actually, as we increased our data collection, it didn't necessarily reduce the variability. Level 3 is actually more variable than level 2. And that can happen, right? If you're if your specific site is a bit of an outlier in your region, then adding more data can sometimes be detrimental, believe it or not. So that's another good excuse for local data collection. It's just that, in general, the more data you have, the better regionally, but nothing beats actually having local data, and even a small amount of that you can use to try to um, correlate with other regional data to get better estimates, essentially. Here's an example of the loading. So this is chloride in pounds for each. This is a year of data in this case, not individual events. Keep in mind this is only during concurrent runoff. So this is when the highways actually has runoff from it. If it's just a dry condition and water running past via the stream, we're not counting that in these calculations. But once again, the general takeaway is that as you add information, the variability reduces, and we have a much tighter amount of, much lower spread in the amount of chloride coming in per year, which makes it easier to kind of estimate how much you're going to have this is a problem from year to year. So a quick rundown of the results. We talked about the particular criterion for chloride. Depending on how much data you use and level of analysis, our exceedance level ended up being either below 0.1% up to 2.3%. And all of these are within the expected model error and around that range of 1.1%. And in general, as you include more data, the range is reduced. So there were kind of three main metrics we were interested in with this study. One is the downstream event mean concentration. So those are the box plots we saw, the box and whisker. It's kind of important because if some aquatic life is more susceptible to persistent concentrations, then these EMCs become very important, right? We also had the criterion maximum concentrations, the CMCs. Those are the water quality exceedances. How often do those happen? Those have a similar detrimental effect on aquatic life, maybe in a different way, and maybe different species are hurt in different ways. So those can be important too. And then, of course, the other thing we were considering is the annual concurrent runoff load. How much chloride are we adding to the system each year? And that is more on the accumulation sides. How does this affect the ecosystem in more of a long-term analysis as opposed to these year by year or event to event analyses. So we had a quantitative analysis of this, but I think the qualitative analysis is a little bit easier to understand, a little more intuitive. As we add different types of data, they had more or less qualitative effect on the results. So depending on what your metric of interest is, you may have a higher incentive to gather specific types of data versus others. So for example, with the downstream event mean concentrations, we found that the upstream streamflow was actually the most important thing to focus on. And if we only had money for one type of data analysis, it would have been the upstream streamflow in this case. I think part of that was due to the increased variability in the streamflow compared to the others in the region, which was, part of that analysis. Conversely, if we're looking at the exceedances, then actually the highway concentrations become the most important. And if we're looking at loading, the precipitation becomes the most important. So depending on what type of question we're trying to ask for this analysis, the different types of data become more or less important, relatively speaking. A couple last slides here. This one is just to kind of put in context the storms we had, or the water years in general. The dark blue line here represents the median for 30 years of data for snow water equivalent. And you can see that in 2019, we were pretty close to that median. The first year of data, we were pretty high, so it was kind of a wet year by comparison, and the middle year, 2018, was kind of low. So we were kind of lucky in that we had like a nice branch of one high, one low, and one medium to look at. If we had all three low, for example, then estimating wet years becomes more problematic. So a little bit lucky in that result. You don't know that coming into the planning of the project. We were also lucky in that ODOT was quite a willing partner. They outfitted their trucks with some GPS navigation systems that would clock where they were and how fast they moved. And also they would physically write down um, when they were um, applying chloride deicer, what type of deicer they were applying, at what rate, and we were able to use those data to calculate loads put on the highway. And that was a nice way to be able to check some of our work, making sure our estimates were, in the ballpark in general, kind of see how much of that chloride being applied is showing up in the surface water. So that was actually a great addition to the project as well, and that's also in the report. So wrapping things up here with some conclusions. Plug for the model itself. SELDM is a great tool for CMCs, EMCs, and loading. It's a little more versatile than I'm making it out to be because we use it for one purpose in here, but it can be used for lakes and other conditions too. So I want to give that a plug. With our study, we found that the EMCs of chloride and magnesium rarely exceed the criterion in this study, with the giant caveat that we're comparing apples to oranges. So they don't exceed it very often, but you'd want to kind of take that into account. In general, of course, the downstream EMCs were much larger than upstream EMCs, which is pretty obvious that highway runoff is a dominant driver in these downstream EMCs of chloride. Level 3 analysis tends to produce less variability, as we mentioned, and then depending on what type of question you have, different types of data will give you more or less information. I'm not sure how transferable this is to different basins because, you may have precipitation that's more homogeneous in a region than what we had here in a more mountainous geography area. So, but having said that, it was still kind of interesting and informative to figure out which ones were most important for this particular study. And lastly, I will talk about some other studies we had. There are two previous SELDM studies that we had in Oregon, not tied to chloride, but just more general use of SELDM. The second one is about nesting watersheds. And then the second part of this project looked at groundwater, actually. So there's a whole different report I didn't touch on at all, where we looked at groundwater chloride levels, mostly up gradient and down gradient of I-5, and also the springs and how those were affected over the course of time. So all the links are here in case you want to pursue those at all. The one I pulled from has this nice green glow around it. This is the report where all the figures you saw came from. And I will end with a potentially funny slide and open up to questions. Thank you for your time.